Okay, that should
Bam.
be video good.
Well, Gabe, it's episode 3.
It is, but I haven't actually turned on the mic, so now we've got a mic on as well.
It's episode 3.
It is episode 3.
The worst Star Wars movie, but the best podcast so far. Let's hope.
I'm trying to enunciate this time. That's the plan.
Right. We're both going to remember, enunciate.
Enunciate, yeah.
Exactly.
All right. Okay, so it's the 5th of December.
Right.
2020.
Yep.
Saturday.
No, Friday.
Saturday.
Is it Saturday?
It's Saturday.
Tomorrow's Sunday. Okay.
Tomorrow's Sunday. That's the way it usually works. And it's 8:25 p.m.
8:25 p.m.
So, why don't you lead us in, buddy?
Yeah, so I wanted to talk today about the beginning of the universe. And the reason I wanted to talk to you about it is because I'm just sort of studying this again for the first time since grade 9 or grade 10 science class. And when we were all there, 10 or 11 years ago in Mr. Maharaj's class studying this sort of thing. So I'm coming back to it, and it's been a long time, so I wanted to talk to somebody who is more familiar about it than me.
Hopefully I can supply that somebody.
Absolutely. So, this is I was reading this book called by Bill Bryson. It's called A Short History of Nearly Everything. It's and the reason why as well that I wanted to talk to you, because I know you try to keep relatively current with this sort of thing, is this book is written or was published in the early 2000s. So
right.
I think around 2003 or 2004. So it might be a little old.
Yes, so there are things that have happened in theoretical physics since then. Big important things in terms of our theories about how the universe began, and in terms of cosmology as a whole. I'm not sure there is anything too radical in terms of the theory side of things. The big breakthrough on that front. Well, the two big breakthroughs have been the discovery of the Higgs boson in 2015, and that was swiftly followed by the first measuring of gravitational waves at LIGO, at advanced LIGO.
Right.
So those are physics things, but let's back up a little bit before we get into that sort of stuff.
Right, exactly, because we're going to start at the very beginning.
For sure.
So something I found was really interesting is that basically the dot of an I, if you're looking at a normal text, like when you write a text, the dot of an I contains something like 500 trillion, or excuse me, I think it's like 500 billion protons. And protons are, of course, one of the particles within an atom. And the universe, at its conception, was infinitesimally smaller than that. Just a tiny, imagine a fraction of a proton, if you can. It's really hard to imagine. And everything that we know in our reality was all stuffed into this tiny, tiny sphere or space.
Yes. So this is a tricky place to start, because this gets real hardcore straight off the bat. The exact size of the universe at the beginning of the universe is something that is a big question mark.
Right.
So, was it exactly that size? I've in my time I've heard anything from incredibly small to nearly infinitesimally small, to sort of the size of an orange. There's this range of very small that the entire matter of everything in the universe was packed within. Right. So what? Exactly how big it was at the time is tricky, and that's something we can explore.
Right. But a term for this that the fellow in my book uses is a singularity. He calls this a singularity. Yes.
So a singularity is an infinitesimal. It's a region of space with infinite density.
Okay.
And it seems to make a lot of sense that what happened at the beginning of the universe was a singularity.
Right.
But singularities are also used for phenomena like black holes.
Right.
And one of the things that you learn is the more you learn about the beginning of the universe is that what's essentially happening is not only is the universe being created, but the very laws of physics themselves are being created.
Yeah.
So we know how much it makes sense to call things a singularity at this specific point of time, or
Right.
it doesn't make sense. It's hard when you're dealing with. So what in the books and stuff that I've read, typically the way people deal with the beginning of the universe,
Right.
Especially like I just read this excellent book that I totally recommend to you by Joe Dunkley, Our Universe. And she specifies that she starts her universe at some incredibly short period of time, sort of after the beginning.
Right.
The beginning, the actual moment at the very beginning of the universe is really confusing and murky.
Right, exactly.
So in order to sort of sidestep that, you always specify that you specify you're an incredibly small fraction of time after that.
No, exactly. And that's why, they have some of the scientists here talk about they're able to conceptualize the universe 10 to the negative 43rd of a second. So that's 110 million trillion trillionth of a second is where they've kind of measured back to. But it's not at the very, very beginning. It's like an infinitesimal or very, very small.
Not infinitesimal.
Not infinitesimal. You're right. 1 million trillionth of a second. They're able to kind of measure back to and talk about from there.
Right. And so to us, that seems like a very short period of time. But that is in the scale of the universe at that particular moment. A lot of things are going on.
Right, exactly. And something I've found was really interesting is in this book they talk about after around a minute and a half or 180 seconds, 98% of all matter in the universe is formed.
Yeah, so this is where things get a little murky for me. Are you talking about the conversion of energy into matter?
Yeah, so he talks about hydrogen, helium, and a small amount of lithium are created at that point.
Okay, got it. Yeah. So traditional matter. Yep, that makes total sense.
Yeah. So 98% of that is created. Around the same time, you have gravity's popping out, followed by electromagnetism, followed by the strong and weak nuclear forces, and very shortly after the Big Bang, those come into being.
Right. So what you're dealing with now is the predominant theory about the beginning of the universe,
right?
Which is something referred to as the inflationary theory.
Inflation universe, right? Yeah.
So we can back up and we can talk for a moment about that. And
do that. Yeah.
The reason why we think inflation happened.
Right.
And it's really quite simple. It comes down to this guy, Hubble, who's renowned for his telescope. But in terms of actually doing science, one of his most famous things is he's the guy who first really demonstrated that the universe was expanding.
Mm-hmm.
So when people figured out the universe was expanding, one of the first things scientists did was go, whoa, if the universe is expanding, we just flip the value of expansion.
Right.
Expansion, if it's expanding at a meter per second or whatever, we can just flip that around,
right? And
then there'll be a compression, and we'll be able to calculate how long ago it was until the universe was all together.
And that makes sense, yeah.
Right. So, unfortunately, there was a problem. The age of the universe, which you can figure out from other methods, didn't line up with the reversed rate of expansion. So if you just took the age of the universe and you winded things back, you ended up with a really big universe at the start of the universe.
Okay.
So in order to accommodate for that, you needed this moment in time where things very, very rapidly got a lot
expanded bigger. Much larger.
And expanded at a rate that's considerably faster than the speed of light.
Right.
So this is part of the reason why people talk about why the inflationary theory involves the rules of space and time and physics breaking down. Because if they didn't break down in the beginning, you wouldn't be able to violate the universal speed limit.
Right, and that makes sense. And it, but when people think of inflation, they might think of everything expanding, but it's not everything expanding. For example, it's, far as I can tell, the space between the Earth and the Sun is not increasing. In a way, or the space between the different planets are not increasing. From what I was reading in the book, you can think about the galaxies and the space between the galaxies growing larger.
So one of the things that's tricky about this sort of thing is that you're putting yourself in a place where we're talking about scales.
Right.
And I talk in other things about the errors of scale, blah, blah, blah. We don't have to get into that, but I just wanted to put a mark.
Yes, talk about that, yeah.
We'll talk about that at some point. But in this particular case, what's expanding in the universe is space itself.
Right.
And the relationship between things in space, they're held together by forces.
Right.
But most of space is empty.
Right.
We think of space as things because we're things.
Right.
But if you zoom out and if you don't compress things, but if you just took the universe and you gathered all of the matter together in the center of it, you would find out you had a very small amount of actual stuff and an absolutely gigantic amount of space.
Right.
So is the relationship between our sun and us being affected by the expansion of the universe? Maybe a tiny bit.
Yeah.
But when you're dealing with the scales of galaxies to galaxies,
right,
that's when that sort of change can actually become apparent. When you can measure it.
You can see, yeah.
Exactly. Through redshift, through the shift of the light.
So let's talk about these kind of fundamental forces, and we can talk about when they're kind of, I like the term you say, violated in order, so that, we can actually, calculate the reason why the universe expanded so quickly initially and then slowed down. Can you talk a little bit about these kind of 4 fundamental forces? And
sure. So list them up for me, and we'll.
So we got the force of gravity.
Yep.
The electromagnetic. The strong nuclear force and the weak nuclear force.
Right. And then there's an additional sort of force that you can throw in there, which is the Higgs field. The
Higgs field. Okay.
And the Higgs field gives mass to certain subatomic particles.
Okay.
So for us, like all of the forces of nature, intrinsic to keeping things going, for us, not something we interact with most.
Right.
So let's hit the easy ones first. Let's do the electromagnetism and gravity.
Right.
So electromagnetism is one of the best known forces. It is basically the force behind everything you think of in life.
Okay.
Pretty much all of it.
Okay.
When you are lifting things, when you are pushing on tables, not just plugging things into a socket and having electricity go through your computer.
Right.
Your ability to interact with things and touch things and lift things and move things, you are just an electromagnetic web interacting with another electromagnetic web.
Okay.
Right. If you remember your chemistry, like the whole basis of chemistry and the way the atoms and the elements all fit together to form larger molecules and stuff. Okay. Everything that's holding this stuff together is just
the electromagnetic forces.
It's just electrons, bonds, covalent bonds.
Right.
It's your real world is created by different electromagnetic forces, and you interact with them in different ways.
Okay.
The colors that you see in things are a result of the way they reflect things based on their own electromagnetic profile.
Right.
Yeah. So that, like, the electromagnetic force is the one that everybody's familiar with, and that's just kind of essential for life.
Right.
So gravity is another one that everybody's really familiar with because it keeps us down. There you go. You got it. So, unlike for the electromagnetic force, where we understand really well that the particles that carry it We understand the electron very well. We understand tons of the interactions between different electromagnetic objects really well. We've never found a force-carrying particle. They're called bosons.
Right.
We've never found a boson for gravity. It's hypothesized there's something out there called the graviton. Never found it.
We haven't found it. Okay.
Gravity is proportionally an incredibly weak force. It's associated with large amounts of matter.
Right.
But so that's why we notice it on things that are huge,
like planets.
like planets. So right now we actually have some level of attraction through gravity together. Right. But if we bring our hands together and then pull them apart, we don't feel any greater resistance due to gravity.
No,
even
exactly.
Though technically, as our radiuses get closer to each other, like they do when you're extending your arms towards somebody.
And if a fly is flying around you, it's not being pulled into your gravitational fields. Yeah, it's not orbiting you, even though it can feel like it is. So
the fact that we feel gravity on the Earth, and that for interstellar travel it's such an important part. Intrasolar travel, something like that. Yeah. Travel between planets and systems in your solar system. The reason it's so important for that, everything is big.
Right.
You're dealing with really big stuff, So those are the ones we're most familiar with. We know probably maybe the most about electromagnetic forces.
Right.
At a certain point, it's hard to tell. We know a ton about them. We know relatively little about gravity. We still know a ton about it, but we don't know anything about its force-carrying particle. If it has one, how it actually does the function.
Right.
We know pretty exactly how electrical things interact with each other.
Right.
We know roughly how gravity interacts with other things.
Right.
But not exactly. That leaves you with two forces.
Right.
What do you know about weak nuclear and strong nuclear force?
I actually don't know very much at all.
So, strong nuclear force is responsible for binding the nucleus of atoms together.
Okay.
So, it's pretty darn important.
Right.
And it's called strong nuclear force basically because it's stronger than the electromagnetic force.
Right.
And we know it has to be stronger than the electromagnetic force because
otherwise the electrons would be ripped apart and an atom would split.
Very close, but the electrons aren't actually in the nucleus. They orbit.
Right, that's true.
So it's the protons.
Okay.
Because the protons are all positively charged.
Right.
Or that's arbitrary, obviously.
Yeah.
They're positively charged and they're all packed together.
Right.
So if the strong nuclear force wasn't there, they would all
fly out.
Eject.
Okay.
Okay. So that's the strong nuclear force. And that one is the one that I probably know the least about.
Okay.
But it is I don't know. I just don't know if it's more of a mystery than I know it's less than a mystery than gravity. I don't know if there's some things we don't understand about strong nuclear force.
Okay.
The one I know a little bit more about is weak nuclear force.
Right.
Weak nuclear force, whereas strong nuclear force is responsible for binding atoms together.
Stuff in the nucleus, yeah.
Weak nuclear force is responsible for binding actual subatomic particles together.
Oh, okay.
It binds protons together, and it binds neutrons. It binds electrons. It doesn't bind electrons together. I lied. It binds a ton of different particles together.
Right.
Those particles are classed into two groups, the hadrons and the mesons.
Right.
The hadrons consist of 3 quarks.
Right.
Examples of hadrons are neutrons and protons.
Right.
And the mesons consist of 2 quarks.
Okay.
And the electron is its own thing, and I misspoke there. It is a single particle.
It is, yeah.
So the weak nuclear force has a very interesting characteristic, and that is that we think of forces as being sort of as pushing things away.
Okay.
If that makes sense.
Right.
Like the electromagnetic force, the electromagnetic force has sort of a push and a pull aspect to it with the poles. But you think of the balance of a lot of things as being repulsive.
Right.
So you think of gravity as being sort of balanced out by the normal force,
Right.
which is just the resistance of the actual object that's putting out the gravity
Right.
underneath your feet. The weak nuclear force, it gets stronger the further away quarks are pulled.
Okay, interesting.
So if you have two quarks in a meson,
Right.
And you're trying to tear them apart,
Right.
the further you get, the more they pull towards each other. It's like an elastic connection.
Right.
And in fact, that elastic connection is so strong that it's impossible to ever have a single quark by itself. And the reason for this is because the more energy you put into trying to pull these guys apart,
Right.
eventually the only way you can separate them is if you create enough energy so that there's an excess amount of energy there so great that it produces another quark.
And that would.
And that bind. So then
you create another bind.
Exactly.
Right.
So
Rather
then
than tearing them apart, you create something that they have to bind to.
Exactly.
Or one of them has to bind.
So if you pull two guys apart, they both have to bind to new quarks that just materialize out of thin air.
Right.
And then they zip off and do their own thing.
Right.
With the rest of the energy.
So is this what happens when they talk about splitting the atom?
Yes and no.
Okay.
Traditionally, splitting the atom refers to nuclear fission.
Right.
Which is a product of the strong force.
Right.
You are getting energy because you are breaking apart the strong nuclear force.
Right.
You're pulling these individual parts of the atom apart.
Right.
In this case, when you are, what it is give you a result from, we touched very vaguely on the Higgs boson earlier.
Right.
What's happening? What happened in order to produce the Higgs boson was we smashed particles together.
Right.
So hard that they tore each other apart. These quarks tore each other apart at such great velocities that they made really big, really rare particles. Because the more energy you have when you're tearing, like if you're just vision the meson pulling apart again,
right.
Vision the meson pulling apart, and the more energy you pull apart with, the higher chance you have of just making a giant particle.
Right. Right.
So the Higgs boson and sorry, what's going on?
Yeah. I did earlier.
Just gonna put that over there. So the Higgs boson is a really heavy, really big particle, 511 MeV, I believe, straight off the top of the head. It's a huge particle.
Yeah.
So that's why it took them so long to try and make it. Because what happened, the Large Hadron Collider at CERN,
right,
which I believe collides neutrons. The Large Hadron Collider at CERN accelerates these things around,
right,
smashes them into each other at high speed,
right,
and then the actual results of each collision are measured by detectors,
right,
and the sort of the sort of product of each collision is super dependent on how the two things actually end up smashing together.
Right.
So you can do your best. It's kind of like you've got a giant wind tunnel,
right,
and you're throwing these like tiny feathers up into it, and you're accelerating them as hard as you can around until you get two that smack into each other.
Right.
And then they explode and a chicken comes out.
Right.
That was kind of like what the Large Hadron Collider was.
Interesting. Okay.
If you were going with a more mechanical metaphor, you're trying to smash two feathers together so fast that a giant fireball erupts.
Right. And it's like, oh, where'd that come from?
Exactly. So those are your four. Those are your four basic forces.
Right. I think that's a really good sort of rundown of what they govern. A sort of entry level, view into what they govern.
Exactly, and they're sort of the essential part of what we call the standard model of physics.
Right. So one thing that's going off of that I found really interesting in this book, they were talking about if the strength or proportionate power of these forces shifted or were different in the beginning, we probably wouldn't have emerged in the way we did as a species on planet Earth.
Yeah, so this
It's kind of like a what if scenario. What if gravity was this much stronger, or et cetera, et cetera? What if it was this much weaker? Would the universe just be like an endless cloud of debris because nothing was holding together? If the force of gravity was weaker, for example. These are just some of the scenarios that, the author is raising after talking to different scientists. What do you think of those kind of what if ideas?
So this is interesting because if you talk, in my experience, when you're talking to physicists, they give this sort of hypothesizing very short thrift.
Right.
And that's because, we don't really know what was going on back then that well.
Right.
It is fascinating to think, if you think of causality,
Right.
the beginning of the universe is this incredibly pivotal point.
Right.
Where the forces that govern our lives today were created.
Yeah.
So in some way, it's kind of obvious that if things were created in a slightly different way,
Right.
You'd end up with a totally different universe.
Absolutely.
So in a way, it sort of comes out how these are things that I think are really fun to think about.
Right.
How useful they are in terms of physics and in terms of ideas about the way the universe actually developed. I'm not sure.
Right. No, absolutely. But they are kind of nice, I think, ideas that sort of catch people's attention who are sort of coming into this, for the first time or second time or whatever, or just they're kind of casually learning about this. This is something that could really get them going and thinking about.
Anything that gets people excited about physics or astrophysics or cosmology is a good thing.
Yeah, no, absolutely. So, in keeping with that, I wanted to talk about just one kind of funny story.
Go for it.
And this was about cosmic background radiation. Mm-hmm. So, really quickly, the way I understand cosmic background radiation, they're microwaves. They're small waves, and they kind of show up like static. They show up like static on instruments, such as your TV screen. In fact, there's a statistic that if you turn on a TV and it's all staticky, he was saying that 1% of that is cosmic background radiation, which is pretty cool to think about. Mm-hmm. But anyway, so how this was discovered was kind of by accident, where these two scientists, Arno Penzias and Robert Wilson, they're studying in New Jersey at a communication disk, and they notice all this static. Mm-hmm. And they try to turn off all their instruments. They try to basically keep everything silent as much as possible, and they still don't get rid of it.
Have you heard of the pigeons?
In the pigeons, exactly. Yeah. Clean up all the pigeon shit.
Yeah, they think they got out there and shot pigeons because they thought it was pigeon shit.
Exactly.
So there's another side of this story. I'm not sure it's covered in your book. So these guys end up with the Nobel Prize,
right,
for the discovery of cosmic microwave background. There were nearby two scientists, there you go, who were actually working to develop an experiment to measure it, and they did not get the Nobel.
No, and they even in their findings said, if we went and studied at the tower, we would probably find it.
The Nobel can be like that. I think with the number of women who have been passed over for Nobels, I'm not too concerned about a couple dudes missing out, but
it just is part of it.
It is what it is. So sorry, what did you want to ask about CMB?
Well, I wanted to talk about so how this idea works is that these are waves of light or microwaves rather, that are from what we call the Big Bang itself. These are as far back as we can
about 100 million years after the Big Bang.
100
pretty damn close.
But pretty damn close, right?
So basically what happens is, let's go back to our picture at the very beginning.
Right.
Everything's packed into a ball, it goes boom.
Yeah.
Right. As it's going boom, matter's being created, blah, 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 blah.
Right.
Lots of things are happening. What's going on in general is you have this sort of fluid almost.
Right.
Everything's incredibly hot and gaseous.
Right.
And light, we're at a very unique time in the universe where everything's still so dense
Right.
that light can't really escape. It just kind of bounces around. It's constantly colliding with things.
Right.
This is really weird for light. In general, light goes on forever.
Right.
And it hits into one or two things and then just keeps on going forever.
Right.
But because the universe now is so empty, light basically just travels forever.
Right.
You know, the lights being emitted by our bulbs and things are incredibly lucky.
Right.
They get to interact with some stuff. In general, light just zooms off into the universe and doesn't do anything for the rest of its infinity.
Yeah.
With the cosmic microwave background, what's happened is at that particular time, all of a sudden, these light particles weren't colliding into things.
Right.
Matter was spread out enough that they escaped.
Right.
Right. So they started traveling straight.
Right.
So the reason it shows up as static everywhere is because do you know how long the universe has been around for?
Yeah, he was saying roughly, which I knew already, roughly 13.7 billion years, something like that.
Call it 14 billion years.
Let's call it 14 billion.
So these pieces of light have been traveling for 14 billion years at this point.
Right.
And that's why they're microwaves. Because they've been losing energy.
Right. Right. So getting smaller and smaller and smaller.
Yeah, their oscillations are
their wavelength, right?
Exactly, increasing.
Okay.
So how you pick up microwave radiation is you just listen.
Right.
And then all the time right now, there's 14 billion year old light showing up on the planet.
Right.
And more. And more. Forever. Right. So that's where the cosmic microwave background comes from.
Right.
It's just, they're at a radius of 14 billion light years away. There was, at the beginning of the universe, light that escaped from this cloud of gas.
Right.
That was then the whole universe.
Right.
And now it's showing up.
Right. And that is just going to keep increasing.
Yes.
Okay.
So interestingly, well, it's just going to keep happening.
It's just going to keep happening, yeah.
So interestingly enough, this happens from microwaves, but you can detect things in different wavelengths that also originated very early on.
Right.
By trying to pick up things that happened that long ago.
Right.
It's just that different wavelengths, it can often be trickier.
Right.
So the people trying to do it in radio waves.
Right.
But you need incredibly large collector of radio waves, and so far we haven't managed to pick up the cosmic radio wave background.
Right, exactly.
Whatever they end up calling
it. Yeah. Interesting. Okay. No, but that's good because that kind of, it's interesting because it's as close as we can get to peer into the past. Think about it that way.
Yes. No, in some ways it acts as sort of a limit. People have ideas about other things that we could pick up, that could originate from that time. But a lot of this just relates to the most basic fact that the particles that have essentially an infinite lifespan, just keep on going.
They keep on going, yeah.
And that we have the ability to measure some of these things,
right. And I think that's a pretty, wondrous sort of capacity that we have. We can kind of understand and have a sort of conscious idea of when you look at a TV screen that a certain amount of that is these microwaves that have slowly, ever so slowly, up until now, just at that moment are hitting us, right?
Quite quickly, but
sorry,
they're old.
They're old. Exactly. I should say they're traveling quite quickly, but they've had a long way to go. So I guess kind of to begin to wrap it up, in this book they're talking about different ideas about the possible end of the universe. Was the universe going to end at some point? Before
we go all the way that far, so we've gotten to a certain point. Like what more really happened in your beginning of the universe? Like what else have you covered? What have you learned in the book?
So we just barely touched on the formation of other elements. So we're talking about, I think I said it earlier, was that about a minute and a half in, or a very short time period after the initial burst, hydrogen, helium, and a comparatively small bit of lithium are created.
Yeah, you can think of it as the hydrogen universe. There's
universe.
trace amounts of helium in
Right.
and even less lithium, maybe.
And hydrogen is basically the fuel for stars. It's the fuel for galaxies. It's the fuel for the big sort of gravity sinks in our universe.
So things start out hot.
Right.
Universe gets bigger.
Right.
Things cool down.
Right.
When things cool down, at a certain point, gravity starts to be strong enough to bind things together.
Okay.
When it's strong enough to bind things together, then you start creating these pockets of matter.
Right.
And these pockets of matter eventually coalesce to form the first stars.
Right. Okay.
Right. From there, the other elements in the universe are a result of bigger and bigger stars being created.
Right.
And those super big stars, they do nuclear fusion. So they fuse hydrogen together to form helium.
Right.
Basically, they're so big that they crush all of the nucleuses together until the nucleuses just decide that they should get together and make something larger.
Right.
And they get bigger and bigger and bigger and bigger,
Yeah.
and they start making more and more elements.
Talk about pressure from your family.
But there's a problem, and that problem is iron. Once the stars are big enough that they're crushing together, so you can think of it as they use them up. They use up all the hydrogen to make helium.
Right.
They use up all the helium to make the next biggest one. I forget exactly what the sequence is. But the sequence ends up with iron, and at iron, they can't make any more.
Right.
They can't crush iron together. The force that it takes to crush iron together is too great.
Right.
They can't crush iron together to make a bigger element.
Right.
So the obvious question after that is, we know there are lots of elements that are heavier than iron.
Right.
How did they come to be?
Right.
The answer to that comes in two ways.
Right.
One of them is that when big stars explode,
Right.
they send out their elements, their iron, their hydrogen, their helium, all of that stuff. But they also send up shards of those elements. They send out neutrons. And if you slam into things with neutrons, then those neutrons can bind and they can turn into a proton.
Okay.
So if you have a piece of iron here and you smack into it with a neutron, it binds and it turns into the next element on the periodic table,
right,
which I should probably know. But whatever. So that's one way they're made.
Okay.
The other way they're made, as far as I know, is that there are accretion disks of neutrons swirling around things, and that those like concentrated areas of neutron activity, they can smack into things and make heavier things.
Okay.
There might be another way, but it's not coming to me right now.
Okay.
So basically, and the reason it has to be neutrons pretty much is because the nucleus is made out of protons.
Right.
So if you're trying to smack a proton into there, it starts to get close. It sees a ton of protons. It zooms away.
Right.
You can smack protons together to make heavier things when you're dealing with fairly small numbers of protons in the nucleus. As you get bigger and bigger, the repulsive force is so strong that it's just too difficult.
Right.
So neutrons, have no charge. They can smack into a nucleus and actually turn into a proton and stick.
And that's how you create something.
Yes.
That's how you create further elements.
That's how you get, all the way up to uranium, basically.
No.
All right, so now we've created the elements. We've got the starts in place.
So the next chapter of my book, which I haven't read, is the creation of the solar system.
Right.
So I was thinking maybe we could hold
off
on that. But
for sure.
Kind of if we want to wrap up, we talked, or if we want to kind of just sort of recap what we covered so far is we covered, the idea of inflation.
Mm-hmm.
We covered the 4 fundamental forces, the strong and weak nuclear forces, the electromagnetic force, and the force of gravity. We talked about kind of how particles are formed, which was really cool. And we delved into the Higgs boson and, why they were colliding these giant particles together because of that, weak nuclear force, where in order to pull sort of protons apart, you have to create something new so they actually latch onto it instead, because the further you pull them apart, the stronger the tether between them is, like an elastic band.
Exactly.
Okay, so that's cool. That's something really helpful for me to understand, because I had never before sort of understood how the particle collider worked and why
how it actually makes particles.
Yeah, how it actually makes particles. Yeah.
No, it's just conservation of energy.
Right. That makes sense. So, and I think the next one we could cover would be, logically, if it makes sense to you, the creation of our solar system.
Yeah, of course, we can do that.
Yeah, on the next one. Yeah.
But so you wanted to do the end of the universe. That's a good place to end.
Yeah, we can end there. Yeah, for our discussion on the universe. Yeah.
So, what have you been told about the end of the universe?
So, not too much, but basically the idea that is the universe. I was just wondering if the universe is slowing down. Is it in its expansion? Is it going to stop? Is it going to lose stability? Things like that.
So for a long time, so when Hubble first discovered that the universe was expanding,
right?
We had a pretty good idea. Well, we thought we had a pretty good idea that would mean that over time, that rate of expansion would be slowing down.
Right. Makes sense.
Yeah, exactly. So you have this initial big explosive event.
Right.
And then for the rest of time, the universe slows.
Mm-hmm.
And that led to ideas about the end of the universe involving things like a big crunch.
Mm-hmm.
So at a certain point, the expansion slows and slows and slows, and then it flips around and it starts coming back in, and eventually it compresses again.
Right.
And this excited a lot of people who were frustrated by the fact that under the model that we use most often to understand the beginning of the universe, the inflationary model,
right.
Under that model, it seems like there's a finite universe.
Right.
And that sort of rubs a lot of people the wrong way.
Mm-hmm.
For reasons.
Right, exactly.
The idea of a big crunch then sort of returns you to an infinite model.
Right.
Because you could think of a big crunch happening, and then everything gets sucked back in.
Right.
And then it all explodes again.
Absolutely.
And then it just goes on forever.
Absolutely.
Unfortunately, as we did better and better research into the actual rate of expansion,
right,
we discovered that the rate of expansion was not as we had thought. It was not as we had thought, slowly going down.
Right.
It was in fact increasing. The universe is getting bigger faster than it was in the past. This is confusing. People are not totally sure why this is. If you've heard of the term dark energy,
right,
this is what dark energy is supposed to be responsible for.
Expanding the universe.
Not expanding the universe, but increasing the rate of expansion.
Increasing the rate at which the universe expands. Okay.
Exactly. So now it seems much more likely that the universe will continue to expand forever,
right,
and it may even expand quicker than it did in the past.
Right.
But we really do not understand dark energy very well.
Interesting. Okay.
There's a classic picture, and if you Google dark energy or if you Google dark matter, you will almost undoubtedly get some sort of pie chart.
Right.
And the pie chart will consist of 98% dark stuff.
Yeah.
And 2% matter.
Right.
And of that 98% dark stuff, I recall about 70% of it being dark matter, and then the remaining 28% is of dark energy.
Okay.
So I've talked to some really smart, really capable physics people who throw question marks up about dark matter and dark energy. I'm not somebody who questions cosmologists.
Right.
If they say there's dark, I've seen a lot of the stuff for dark matter, and I'm very convinced by the fact that there's dark matter. It seems to be the consensus that it exists.
Right.
this might be a topic for another time.
Yeah.
I don't know.
Yeah, maybe we can delve into that a little bit, because that, I think, if I want to get a little bit more of a sort of a base comfort level with the sort of building blocks of physics,
before you jump into dark matter. Dark matter is fascinating.
Yeah, and I'm excited to learn more, but it might be good to get a bit of a foundation first.
I know 3 good theories that for what it could be.
Okay.
I know much less about dark energy, except for the fact that it's supposed to be responsible for the increased rate of expansion.
Interesting.
So now, in the old days, there were a lot more theories about what would happen in the end of the universe.
Right.
But one of the things that's nice, I think, about dark energy is it throws that into question again.
Right.
We're really not sure. It seems a lot more likely these days. If you watch science TV education shows,
right,
or whatever, that they will, and they go into the end of the universe, they'll almost always posit something where everything gets colder and entropy occurs and the whole universe stretches on and on and on for endless amounts of time, and all the stars burn out, and at a certain point everything's just dead and barren and freezing.
Right.
And how right or wrong that is, the time lengths are absurd.
Right.
Like many, many, many times longer than the entire length of the universe so far.
Right.
And to a certain extent that seems right. We do seem to be at a fairly young point in the universe, which is kind of remarkable. Our planet and our solar system,
right.
Our planet is about 5 billion years old. So it's only a third the age of the universe.
Right.
And the solar system. Oh man, sorry. Our star. I can't remember. Oh well, next time.
Yeah, we can talk about that next time when we get into the creation of our solar system and our star.
Yeah, but
that was good.
So yeah, the that sort of wraps the end of the universe.
Yeah.
I'll do my, because at the end of these things, we're always trying to send a message to our future selves.
Definitely.
I am always super excited to see what's going to happen in cosmology and in physics.
Right.
It's great in many ways because it's a big old guessing game.
Yeah.
I would like to see a lot more money in these things.
Yeah.
A lot less money in killing people, maybe.
Right.
That seems like a good place to take the money out, in my opinion. I would like a better picture of the overall theories beyond the standard model. So for me in the future, I want you to know, is supersymmetry the big thing? Is that did that hold on? Because right now everybody still thinks that supersymmetry is pretty sick, except for those crazy guys who think string theory is the bomb, and they still haven't figured out how to actually measure any of that in my lifetime, as far as I can tell. So I would like to see some real evidence towards a model that advances significantly on the standard model. That 5, 10, 15, heck, even 20, 25 years. I'll give them that long. That's the big breakthrough for me.
Absolutely.
So what about for you, man?
Yeah, I want to kind of bring it to the solar system level, and I want to see in the future when we're looking back at this, has someone gone to Mars yet? Has someone...
Oh, this is a great question.
Yeah, have we actually set up a little base camp on Mars? And what kind of shape is that taking? Is there, regular intrastellar travel within our solar system? Can we go into space?
Oh yeah, totally.
I want to see if that's possible, or if it is happening, and if we have even gone when we look back at this.
And I guess I'll wrap this with one last question. Is there life in the solar system apart from us? Microbial life? We don't think there's anything big out there, but any evidence of small life.
That's right.
And build lots of telescopes, because they're going to be sick.
Yeah, I want to see better telescopes too. All right.
All right, buddy. Thanks so much.
Thanks, man. Yes. Good job.
And I'll turn off that sound. And this thing didn't look like it cut out either.
No, it looks like it stayed.